So class, we left off at memory mapping. That's where we will continue from. Now we will be dedicating an entire week to the system calls related to the management of memory. And one of the most important system calls in that family of functions will be mmap, short for memory map. It is a very powerful system call in the sense that it can create new memory mappings in the memory space of the process that is executed, that system call. Now, what exactly is a memory map? Well, basically, mmap can help us to very efficiently read a file or a portion of a file from the hard disk and very rapidly, very efficiently place it, all of those contents, in a region of the memory that we have designated. In fact, this is the system call that is used behind the scenes by the operating system, by the kernel, when you execute a new program. So that program, the executable file, is located on the hard disk, containing all the binary instructions, static global variables, and so on. So when you execute it, it has to be placed in memory, to RAM. Of course, creating the necessary heap, stack, text segment, data segment, and so on. So it is the mmap system call that is used behind the scenes in order to very efficiently take portions of that file. So for example, the binary instructions from the executable file, and place them very rapidly onto a corresponding memory location in RAM. Now that is what we denote by file mapping, and there is also anonymous mapping, which doesn't have a corresponding file. And instead, as it says, the pages of the mapping are initialized to 0. So you can use it in order to create additional memory locations, and it provides you a wealth of options in order to manipulate them. Now, we will talk more about memory mapping when the time arrives, and we will see that it can be used in order to accomplish communication between processes. And how can we accomplish that communication? Well, simply, for instance, by creating a shared memory location between processes. Remember what we said. Processes cannot communicate directly. Processes cannot access the memory spaces of each other. They cannot read, they cannot write, they cannot even see which memory spaces are allocated by which other processes. In fact, truth be told, even its own memory space is invisible to the process. It can see the virtual addresses, but not the physical address. So it has no idea where it is in memory, and it has even less idea of where the other processes are located. So among the many options that are available for communicating between processes, and by communication I mean sending and receiving data, one of them is through memory mapping. So basically the idea is that these processes that want to communicate, they ask from the kernel to create a memory location that will be accessible to both of those processes. So if they make that request and the kernel grants that request, in that case, whatever one process writes to that region, the other process can read it and vice versa. So we will see that mmap can be used for this purpose in approximately 3 to 4 weeks. And this brings us to the topic of static and shared libraries. Now, I'm sure that you have talked about libraries during your first year and second year when you were learning about compilers. And well, before making that assumption, I should be asking you, you have talked about libraries, right? Shared and static libraries. This is not the first time that you're encountering them. Yes, no?
Not in depth, but yes.
Okay. Well, we are not going to get into depth either, since they are not really a kernel topic. However, the part that concerns us is the distinction between the two. Now, what is a library? A library is just a collection of function code. It's a collection of functions. Now, it can be an object library, denoted as either a static library or as a shared library. Either case, it doesn't contain any source code. So what's the difference between static libraries and shared libraries? Now, the main idea, the main issue that is addressed by these libraries is very simple. The question is, how do I include, how do I integrate into an executable that I'm creating code that I haven't written? For example, printf. So how do you include it in? Now, with static libraries, the idea is very simple. At compilation time, as you know, there are multiple stages to it. First, the preprocessor and so on and so on. And at the last stage of compiling, if you remember, there was the linking stage. Now, the linking stage, whatever functions, such as printf, so whatever functions from the standard C library or whatever system calls you have called in your program, it is the linker, that executable, that is responsible for locating in the file system where that code, that compiled actual code, the code for printf, is present. It finds it, and the code of printf is included, integrated at the last stage of compilation into your executable. So you can take that executable, place it somewhere else, and the code of printf is included inside your executable. So that's what we're talking about static libraries. In that case, I mean, if this is what we're doing, that means we have used the static library containing the code for printf or any other standard C function or system call. On the other hand, there are, of course, the shared libraries. So why do shared libraries exist if we can accomplish our goal with static libraries? Well, the problem with static libraries is double. First of all, if we use static linking in order to create our executables, that means, for example, if we proceed from the example of printf, if you have 100 executables using the code of printf, that means the code of printf is included in every single one of those executables 100 times. So that means a lot of code duplication, the same code present in all of those executables. And that, of course, leads to a waste of memory, a waste of resources. A second disadvantage of static linking is, of course, the fact that if by any chance somebody decides to update the code for printf, so if we have a new version of printf in our static library, that means in order to update all of the executables using printf, they have to be recompiled, all of them, against the new version of printf in that library, because all of them contain the old version of printf. So that means a lot of recompiling. And due to these two reasons, people came up with the shared libraries. Now, the shared libraries have been designed to address these two problems. And the idea is very simple. Basically, instead of containing the code to printf or any other standard C library or system call inside the executable, what it simply contains is the address, the location, the file name of where to find that code in the system. And when you actually execute the program, when the time arrives, when you actually execute the program, and it is time to execute the code of printf, since it is not present in the executable, it uses that information, that location information inside the exe file. So go to this address, to this file name, to this location in that file, to this offset. It uses that information to go to that location and get that code from there dynamically. So we are talking about not static linking, but instead runtime linking. So it is at runtime that it resolves where that code is taking place. Now, where does it look to? Where does the system look to? Where does the kernel look to in order to find those shared libraries? It uses the environment variable LD library path. And how do you recognize shared libraries? You will recognize them in your system. They will be located inside the lib directories. You will recognize them by the SO extension or either extension, or it will be a part of their file names. So I'm explaining this just so that we are all on the same page concerning static and shared linking. We will talk about that in more depth in the future. And this brings us to one of our last topics and one of the most important ones, IPC and synchronization. IPC is short for inter-process communication. So communication between processes. How do you transfer data from one process to another? Why is this a problem? Because it is forbidden for processes to access each other's memory. So how do you solve that? Well, the kernel, fortunately for us, provides us with multiple options, methods of communicating with one another, and they all have their own properties, their advantages and disadvantages. But of course, if you can communicate between processes, that means also there will be synchronization issues. For example, imagine the following scenario. You have process A that wants to communicate with process B. Process A wants to send data to process B. What happens if process B tries to read the incoming data before it has been sent? Now that's a synchronization problem, because normally process B must wait before reading until process A has sent something to it. This is what I mean by a synchronization problem. Now, of course, at this point, you might say, yeah, Ojam, I mean, why do you worry about inter-process communication? I mean, there's a very easy way of solving it. For example, we can just agree two processes on a certain file on the hard drive, and one of us can read to that hard drive, and the other one can read from it. I mean, it's a very simple way. I mean, as long as you know to which file you are supposed to read, to which file you're supposed to write, and from which file you're supposed to read, it's very easily solvable. But then again, using the hard drive in order to solve this issue, it is possible, but of course, as you can imagine, it is highly, highly inefficient. Why inefficient? Because the hard drive is a mechanical device as opposed to physical memory and as opposed to the CPU, and as such, it is many orders of magnitude slower with respect to them. That's why never, ever use the hard drive for such communication purposes, unless you want your program to be extremely slow. What are the methods that are available for inter-process communication? Well, some of them are more powerful than others. So at the first line, we have signals. Now, signals, as we will see very soon, next week, in fact, are a very, it is one of the IPC methods that students really dislike, truth be told. And it is a very basic, very simple, and often insufficient form of communication. I mean, you cannot use it in order to send any data or receive data. You can only use it in order to signal from one process to another that something has happened. Maybe an error or some other condition has been satisfied. There are also pipes, another method, and FIFOs, same idea, which can be used in order to transfer data between processes, but only between processes on the same computer and often between processes that are related. So by related, I mean where one process is the parent of the other. Then again, we have sockets, which is the most generic form, most general form of communication between processes, and it can be used in order to transfer data even between processes that are on different computers. So even right now, while I'm talking to you, my computer is using sockets in order to communicate with your computers through, of course, the servers of MS Teams. There is also file locking, message queues, semaphores, shared memory. These are all methods that we will take a look, except for message queues. So we will study all of these except for message queues. Why? Because they are too old, honestly. Very few people use them anymore. So that's why message queues will be exempted. Now, signals, if we have talked about them just a little bit, are often referred to as software interrupts. Basically, the idea is that a signal can be sent from one process to another. It can be sent from the kernel to a process. And the whole idea of a signal is that it just says that, hey guys, something happened. That's all. And what happens when a signal arrives to a process? Well, basically, one process tells the kernel, Mr. Kernel, I want to send a signal to process with identity number 678. Which signal? Signal number 9, for example. The signals have some numbers. That's how they are identified. The processes are identified by their numbers. And simply, one process through the kernel can let the other process know that signal number 9 has arrived. That's it. There is no information that is transferred, only somebody that is signaling. Somebody, you can imagine it as if somebody is waving. Biri sanki el sallıyormuş gibi. As if somebody is waving to your process. That's it. No information, no nothing. Just a signal. Bir işaret. Now, when a signal arrives to a process, so when somebody waves at you, another process, so when a signal arrives, what can happen? The process can choose to ignore that signal. The process can be suspended. If it was suspended, it can be resumed by that signal. It can do nothing, or even it can be terminated. In practice, most of the time, in 99% of cases, signals are used in order to prematurely end processes, in order to let them know that an unexpected event has taken place and that they have to terminate. That is the most frequent use of signals. But they can be used also for synchronization. We will take a look at that, thanks to some very specialized system calls. Now, something very different between the Windows and Unix operating system families is that in Windows also you have signals, but it is a much more gentle process. It's a much more voluntary process. Let's say that you send a signal to a process and you want to terminate it. For example, when you open up your taskbar and you click End Process. When you click on End Process, basically what is happening, the kernel is sending an end process signal to that process. So basically, it is telling it to terminate itself. Now in Windows, the process can choose to ignore that signal. I mean, I'm sure that you have experienced it. Sometimes you click on End Process on Windows and it is not ending. Whereas in Unix and in POSIX compliant operating systems, processes do not have that option. When you send the kill signal, when you send the signal to stop, terminate a process, it takes place immediately. So there is no avoiding it, postponing it, ignoring it whatsoever. That's one of the important differences between the two operating system families. Towards the end of our semester, we will also talk about threads, which enable us to have multiple flows of execution under the roof of the same process. Because the alternative is to have multiple processes. Of course, we can have multiple processes. We can have 2 of them, 4 of them, 10 of them, 20 of them. You can have as many processes as you want. And all of them can be executed in parallel. But the problem with multiple processes is that it is expensive to create them. It is not very efficient, memory-wise and CPU-wise, to create multiple processes. It takes time. And if you need 10, 20, 30, 40 of them, it is a much better idea to use threads, which is another solution for having multiple flows of execution, but under the roof of a single process. A further advantage of threads is that it is very easy to communicate between them. Why? Since they exist under the roof of the same process, all of the threads, they can share the same heap memory space. And on the other hand, they have their own stacks. So whatever you write into a global variable in one thread is visible to the other threads as well. We will see that there are some specialized tools for synchronization between threads, such as condition variables, monitors, and mutexes, whereas there are other tools available for synchronization between processes, such as semaphores and file locking. At the end of the semester, we will also focus on the client-server application paradigm, which is the most predominant computing paradigm in the world at the moment, where you have one server responsible for serving multiple clients. So one server where you have a process which waits for connections, which waits for requests from the clients and responds to those clients. We will see what is the proper way to implement a client, what is the proper way to implement a server, what are the issues to pay attention to. And if we have time, I will also talk to you about some peer-to-peer applications, which is gaining a lot of momentum in the last few years. We won't really talk about real-time applications, but it will always be a consideration during our lectures. By real-time, basically we mean that the response of one process to a request, to an event, to a signal or whatever, is guaranteed to be delivered within a certain deadline. That's what we mean by real-time. Now, real-time responsiveness is not an oftenly encountered requirement, but sometimes in automated assembly lines, ATMs, and especially in aircraft navigation systems, it is a mandatory requirement. And so you need to be knowledgeable about what you can do in order to achieve this requirement. So we will talk about that stuff as we advance through our semester. Now, class, this is the end of today's slides. The slides are available in MS Teams. What I would like to tell you as a last parting note is that, of course, you will have the homework this week. You will probably have one next week. But I am kindly asking you to make sure that you take the time that you have, whatever time you have available this week, and make sure that you have at least one natively installed Linux system at your disposal. The distribution doesn't matter. It can be Ubuntu or whatever you like, but make sure that it is natively installed, which means no virtual environments. In fact, what I would recommend to you in order to avoid the problems that students encountered in the past semesters is to have access to at least 2 different systems. For example, one can be yours, the other one can be of your friends or the machine at the lab. And whenever you intend to send me or submit a homework, it will be a very good idea if we test your homework, not only on your machine, but also on some other Linux machine. Because I will be evaluating your projects on my own machine. The assistants will be evaluating your homeworks on their own systems. And the key term, the key concept is portability. That's why we are focusing on POSIX. That's why we are focusing on having portable solutions, portable pieces of software. And that's why they will be tested on distinct machines. So if it works on your system and it doesn't work on ours, that counts as a failure. So in order to avoid that situation, what I'm kindly recommending you is to test your software in as many systems as you want, as you can. Now, Mr. Dervish has asked, what is the difference between a virtual machine or native Linux? Well, even though in theory, a virtual machine is supposed to be running exactly as a native system, in practice, unfortunately, that is not the case. And in the past, 2-3 years ago, we encountered several cases of homeworks and midterm and final projects where it was running perfectly well on a virtual machine, but it was failing on a native distribution, even though it was exactly the same distribution. That's why there are still some issues dangling, some issues still left with the virtual machines that haven't been yet resolved. That's why in order not to get stuck on those, in order to get rid of that possibility of bugs, I highly recommend to you to have a native Linux installation. At least that will be one less thing to worry about as far as you are concerned. Any questions?
There is a question.
Who is that?
Darwish Alduman said, what is the difference between VM and native Linux?
Yes, Mr. Osman, and I just responded to that question.
Yeah.
So, any other questions?
Can I ask a question?
Who is that?
Ezgi.
Yes.
Ezgi. Like in operating systems, can't we use a virtual machine on our computer, also in assistant's computer? Wouldn't it be better?
Mrs. Gay, I just answered that question. And I kindly ask you not to use virtual machines and have native Linux installations, please. It will be a source of problems. for both you and us.
Okay.
I want to ask a question. macOS is very different from Linux.
Well, it is not as different as Windows is to Linux. But macOS, as I explained in the first slides, is POSIX certified.
Okay.
Whereas Linux is mostly POSIX certified. And that's what matters to us, POSIX compliance. Your objective will be to develop POSIX compliant code, not Linux code, not macOS code, not Windows code, but POSIX compliant code, so that the code that you will develop, that you will design, that you will implement, will be able to run on any POSIX compliant system.
Okay, I
So we are
understand now.
striving for portability. Yeah. Any other questions? Okay, class. In that case, I recommend that you have a recent installation. Don't use compilers from 10 years ago. Have a recent native installation with updated compilers, GCC compilers. All of the code will be C code. There will be no C++ in this course. Yep. Anything else? Mr. Mohammed Ashraf says, can we say a thread is a child process or a child process or parent process? No, we cannot say that, Mohammed Ashraf. A thread is a thread, a process is a process. A process can have children processes. In that case, there is a parent process and children processes, but threads live inside a single process. So they are not mentioned as children in any way. There are no parent threads or children threads. There are only threads that have been created by a process. And that process can't have a parent process. In fact, all processes have parent processes except for the init process, which is created by the kernel. Other questions? So class, as I said, make sure that you get your native Linux installation taken care of this week before we start the homeworks next week. Gain some time. Make sure that you can get the textbook and start reading it. And if you have any questions about the book, about the lectures, about the course, about anything, you can always, of course, send me emails directly, and I will try to answer them as soon as possible within the working hours. The assistants for this course will be Ümit Murat Akkaya and Efkan Duraklı. I will write their names into the syllabus and update the syllabus on the Teams page. Now, can you, just a question from me, can you access the lecture videos on MS Teams as they are in the chat? Or do you want me to have a separate tab for them?
A separate tab would be easier for us to find, but we can search for it and find them.
And when you search and find them, can you access them? Can you open those videos?
Yes, I just tried and it works.
Okay, excellent. Okay, class, that's all from me. Thank you for your attendance. And if everything goes all right, I will see you next week, Wednesday morning.
See you.
Take care. Mr. Umut says, can you upload all the chapters of the semester to Team? All the chapters? I will not upload the textbook, Mr. Umut. It is up to you to get the textbook.